So hello everyone. We are many people here. We are happy to have Kruti Sudarshan. Will present radiation hydrodynamical simulations of protoplanetary disks. So you can start whenever you want.
Thank you so much, Rafael, for introducing me and also inviting me for giving a talk at the Accretion-Ejection seminar series. I've been following it on YouTube, and it's very informative to have these talks online. I will talk about my PhD work in radiation hydrodynamics, the efforts we've been putting to model the temperature structure of outer protoplanetary disks. I am Kruti. I'm a final year PhD student at the Max Planck Institute for Astronomy in Heidelberg. And this work is in collaboration with my supervisor, Mario Flock, and some other people here. Um, and this work would not have been possible without their support. So I'm just going to start off with some motivation. So we see a lot of substructure when we look at the protoplanetary disk observations. And this has been looked at from the 1996, where we had the first images of protoplanetary disks with the Hubble Space Telescope, to now in the midplane tracing bigger dust grains with ALMA, and the scattered light with smaller grains with VLT. And we've also recently been getting a lot of spectra about the inner disk with the James Webb Space Telescope. So we see that all in all, protoplanetary disk observations show ubiquitous substructure. So these spirals, rings, gaps, also asymmetries, vortices in some cases, and the vertical structure as well is very rich. And we think that some of the substructures here have our origins are originated due to planets. So planets are clear drive clear signatures of these substructures. So they drive spirals in the disk and they open up gaps for large enough planet masses. And we're at a point where we're able to observe some of these protoplanets as well. So we have two confirmed observations, or three planets between two different systems of PDS 70 here, where we have PDS 70b and C. And as of last year, we also have the WISPIT 2b planets. And we see that these are directly imaged in scattered light, and they're also ALMA signatures, but we see that there's clear substructure around them, gaps and rings driven by them. But planet formation models often invoke pressure bumps as dust traps. So they typically require like pressure bumps in the disk where you can trap the dust to even grow a planet. So this brings about this chicken and egg problem of whether the planets are driving the substructure or you need the substructure to grow dust, right? So we have to look at inherent processes within the protoplanetary disk that can also drive these substructures. And these are typically disk instabilities and misaligned inner disks. Some of them can drive substructures as well. I'd like to reiterate by showing this gallery here of the ALMA view in the midplane, showing the bigger grains and the surface in the scattered light that traces the small dust, to show that especially rings are very, very common in these disk observations. And one of the problems that I'm trying to address is whether we can drive these rings by thermally driven processes. I would like to say that yes, we know of some processes that can thermally drive substructures. For example, if you have a misaligned inner disk that can cast these white shadows in the outer disk, and you run radiation hydrosimulations, you find these spirals in scattered light, and there's even some long-term implications in the midplane, forming these rings and even sometimes vortices. And I show these two simulations because these synthetic observations from these radiation hydro simulations are the most realistic, in the sense that they include a lot of physics. And to actually resolve the temperature structure correctly, we need radiation hydrodynamics. So I'm going to explore one other thermally driven substructure scenario. But what I want to reiterate is that we need radiation hydrodynamics to accurately capture the temperature structure of these protoplanetary disks. So let's go back a little bit and try to understand what the outer disk looks like. So we know that the gas pressure causes the outer disk to flare and vertically expand from a midplane. The outer disk is mostly starlight heated, and hence you have this instead of a conical disk, you have this flared bowl-shaped structure. And if you look at the observations of the scattered light of the small dust, you see these bowl-shaped images that clearly show that, we see this flaring also in the observations. Something that's very interesting to us is in the IM loop case, for example, are these little ripples that we see within the flared disk and whether we can drive them naturally by starlight-driven shadowing. And that brings about to the process that I will talk about, which is the thermal wave instability. This is also known by the irradiation instability or the self-shadowing instability in the literature. And this has been talked about since we knew that the disks were flared. So since the Chiang and Goldreich 1997 papers and subsequent papers, we've known that the flaring dissolution may not be stable in all scenarios. What this instability says is that if you have perturbations at the surface of the disk, then you can drive thermal waves that form and propagate inwards. I'd like to show this particular schematic for you to understand how this process works better. So if you have a perturbation at the surface of the disk, the inner side of the perturbation now is exposed directly to the starlight, and hence it heats up and it vertically expands outwards from a simple plane. And the region directly behind it is now shadowed, and hence it cools down and contracts, causing this front here, a thermal wave here. And then because of this thermal wave, there's a region behind it that is directly exposed to starlight, and it causes these sets of thermal waves in feedback that form and propagate inwards if you work out the linear theory for it. And if you look at how these bumps look like in models, these are 1.5D models. What I mean by 1.5D means it has radial wave propagation, but radial vertical radiation transport, because that is really essential. And if you look at what these look like, if you trace the midplane temperature at the left-hand side of this plot, you see that throughout the disk, you can form these temperature bumps that form and they travel inwards at the order of orbital timescales of the disk. And what's really interesting is now that if you trace the surface of the disk, it is not a smooth power law anymore that would be the flared disk solution, but you see these staircases that form. And these staircases are not stationary in the 1D view of the instability, they move inwards of around the order of orbital timescales. So we typically call them staircases or steps in the optical surface. And can we observe these kind of substructures that are driven by the thermal wave instability is a question we'd like to ask. So these 1D models predict that, in fact, we can get these ring and gap pairs that are in the intermediate disk regions, and the fractional separation of these ring and gap pairs are very comparable to the observed D-sharp ring gap pair values that I showed earlier before. And they also say that we can drive signatures in the midplane. And some models say that these produce a pressure maxima that can now actually form dust traps to collect pebble-sized particles. These are some more simulations from Watanabe and Glynn. This is a semi-analytical model where you can clearly see how when you normalize with respect to the thermal time, these waves form and they start moving inwards. One caveat or not just one, so there are some caveats to modeling this in 1.5D or 1D. That is, most of these models are vertically isothermal. What that means is anything that happens at the surface of the disk is instantly, then the information is propagated to the midplane. And this is not actually realistic because you need to assume for a vertical radiation transfer, it happens at a certain time scale that's not instantaneous. And most of these models are also hydrostatic. So what about vertical radiation transport and what about 2D dynamics? How does this affect whether this thermal wave instability is even realistic for disk scenarios is a question we try to answer. And we use 2.5D, so 2D axisymmetric, self-consistent radiation hydrodynamical models, and we try to address this particular problem. We use a two-step approach. So first we have these hydrostatic simulations, And the aim is to try and find a steady state and try to see if there is a steady state for such a problem. So we iterate between the densities and the temperature. So we go beyond between the radiation transport and hydrostatic equilibrium, iterating them. And this is our hydrostatic simulations. And then we also do radiation hydrodynamics, where we evolve the mass momentum energy equations over very long time scales. Here, of course, this is our most realistic scenario. We have radiation transport coupled with wave propagation. This is very important to study these staircase features. Of course, we want to be sure that we're doing radiation transport correctly. And when we always talk about these two different limits, right? The optically thick diffusion limit, where you have a lot of material and hence you're in the diffusion limit where you can't just trace the rays. And there's also the free streaming limit, the optically thin limit, where you can basically capture the individual photons by ray tracing them. We need to make sure our scheme kind of captures both of these limits. And radiation transports is done differently in disk simulations. So you can typically do this Monte Carlo approach, where, for example, like the RADAMC 3D approach. But the problem with RADAMC 3D is it's not very realistic to couple Monte Carlo methods with hydrodynamics, 3D hydrodynamics. The relative cost of computation is extremely high. And of course, we want to do proper hydrodynamics, not just hydrostatics, and hence we move towards other methods. So there's also the short characteristics method you can use. But when you try to solve these energy equations, what you typically use are these flux limited diffusion, M1 closure, variable Eddington tensor kind of approaches. And there are different pros and cons to using the different methods. So I'm going to be talking about the flux limited diffusion closure here. And essentially, to solve your radiation energy intensity, this is a complicated function of position, time, angle, and frequency. So we can break the radiative intensity into different moments. And the moments are typically the radiation flux, the radiation energy density, the first one, the flux is the second one, and the tensor. And you can keep writing these moments, and you can use a closure for the first and the second moments here with the energy density and the radiative flux. And this is what is our flux limited diffusion approach, where you only solve the scalar radiation energy density, assuming for a closure for the radiation flux. And we use a frequency dependent irradiation solver, as in the starlight heating is now frequency dependent, but the radiation hydro itself is gray and flux limited diffusion approach with the PLUTO code. And I'd like to reiterate that the starlight heating is one of the most important aspects of this particular problem, and hence we use temperature-dependent dust opacities for different frequency bands. We have about 130, and then we solve for this irradiation flux from the star as a source term on the right-hand side. And these are basically the Planck mean and the Rosslyn means we get that then goes into the gray flux limited diffusion. I will start with my results. This is results for the hydrostatic case. For my fiducial model, what we see is that these temperature bumps form and they propagate inwards, exactly what was expected from the 1D hydrostatic simulations. We get the same thing in 2D now. This is more clear in the temperature structure. Also in the density, you can see the temperature bumps form and propagate inwards. And if you now plot the irradiation source term, which is the divergence of the irradiation flux, what you see is that these staircase structures are very prominent, and these are the tau equals 1 surfaces. The blue lines are the tau equals 1 surfaces for the different frequency bands from the star, and the red line here is the tau equals 1 surface of the disk's own emission. And we see that these are not strict power laws anymore. These are staircased structures. And the green line here is to indicate the gas scale height of the disk, so it's quite optically thick here. And of course, we want to try and now look at what happens when we switch on radiation hydrodynamics. And what we see is that the inner bump grows. There's some changes between the staircases, but the inner bump grows. And then as a result of it, there's a second bump that is forming behind that also is there for very long time scale. So I run it for 510,000 orbits of inner orbits at zero point 0.5 AU, and we see that these are sufficiently long diffusion timescales, and we see these steady staircase-like structures that are forming and settling. This configuration, as I said, is stable for several timescales. And if you look at the midplane temperature, this is the midplane view in 1D against the power law. The background power law has been normalized, and we see that the bumps initially grow. The first bump grows a lot, and then there's a second bump, then that's driven. And after a certain point here in this model, after 500 orbits already, you get this very stable the staircase sort of structure. And now the second plot, where I plot the radial temperature gradient, we see that, of course, there's where the shadows are, you see modulations in the radial temperature gradient. But something I need to note here is that the radial temperature gradient is never inverted. So these bumps in the radiation hydro 2D case, they seem to be not as strong as what was predicted in the 1D case, where they always said these were temperature bumps. So they were inverting the temperature gradient. And this is not the case in our fiducial model. So indeed, 2D changes a lot. 2D radiation hydro changes a lot. And we should be very careful while making claims for synthetic observations just from the 1D simulations. We should really look at how this changes with proper radiation hydro. Of course, we want to try to push the limits a little further. So we have a model here where we have a surface density of 2,000 grams per centimeter square at 1 AU, which is more of a minimum mass solar nebula like case. And we see that in the hydrostatic case, we drive more bumps now. For the optically thick case, there are 3 bumps and also a 4th one if you squint your eye. But in the hydrodynamical simulations, we have these 3 bumps that form and stay also for very long timescales. Shadows are much more pronounced in the optically thick case. We see that the temperature deviations are much higher, and you see 1, 2, and a 3rd shadow against this green line, which was the fiducial model with the 2 shadows. Here, when I plot the radiant temperature gradient, we see that for the first bump, it's inverted, but for the rest of them, it's not. So the rest of them are still less pronounced shadows. And there is some inward motion here, but these are not similar to the inward motion that was predicted in the 1D case. So this is more of a steady staircase-like scenario overall. Something that we should be careful about is whether this process is entirely spontaneous, which is a prediction by the thermal wave instability, or we have something that seeds the first shadow. And one thing that we noted in our computational domain is that with the frequency dependent dust opacities we use, we have a 10 micron silicate feature here. This is included within our computational domain. So the temperatures from this particular for this particular frequencies correspond to over here where the first bump is forming. So we think that maybe if you can have opacity transitions in the disk, this is a favorable part of the disk to sort of initiate or seed such shadows. And of course, the secondary and the tertiary bumps that come behind it are very natural consequences of then the starlight-driven shadowing downstream. So indeed, the first bump seems that it's matching the 10 micron silicate feature. So we think that this might be a seed for this particular process. And one more thing that I would like to mention is that the initial condition for the inner disk for these irradiated disk studies, it's largely unknown. It's largely not constrained because whatever happens in the inner disk is going to have at some point an effect on the outer disk. So whether this is a smooth inner disk, or we know that it's not smooth while from Mario's work and from works where there are outbursts in the inner disk. So definitely the inner disk condition is not known. So we need better constraints on that. And one of the things that we assume is, of course, the initial optical depth at the inner disk part. So because we only look at the outer disk here, so we need better conditions as to what the initial optical depth is. And we saw that in certain cases, having different radial slab-like models or integrating the radial optical depth, we can see that we find certain hotspots we can create for the first bump. But now that being said, the second and the secondary and tertiary shadows are naturally driven by starlight shadowing. And this is quite different from the 1D linear theory picture that was previously mentioned. And hence, it's really important for any of the processes that has been looked at in 1D to for clear studies in 2D to see whether this is even realistic. Of course, when you have these rings and gaps, one of the things you think about is whether these have observable implications. So here I'm showing you H-band images of my simulations, my fiducial model with RADMC 3D. This is VLT sphere-like, so 1.65 microns, and we see that there are two signatures here. There are two ring gap pairs corresponding to the two shadows we find in the hydrodynamic case. It's also been convolved with a Gaussian beam. And these are preliminary, but I'd like to show that these are probed much better in higher resolution with future telescopes like ELT METIS, where if you look at the beam size, it's really small. So we're really able to probe these rings in very high resolution. And this would be very exciting for us to then probe these scattered light observations in the near future when the ELT is coming up. So indeed, for the substructures that are being driven surface in, this is a very nice process. It's a very natural process of driving shadows. And you will then ask, what about the midplane? What happens in the midplane? Of course, here the first two plots, this is the flaring angle and the surface scale height. So you see these are clear signatures of the surface substructure. But if I plot the midplane pressure gradient, I do see that there are deviations that are at the shadow locations, which means that there is an effect on the midplane pressure gradients, not significant enough to actually invert the pressure gradient to act as a proper dust trap, but maybe we can still slow down some dust at these shadows, more towards this dust traffic jam scenarios that people talk about. So this is still very interesting for midplane structures. Of course, we are now in our simulations, we're modeling a large computational domain. So when we plot the cooling timescale, we see that in the outer disk regions, we drop below 0.01 with the cooling timescales. It's mostly dominated by the optically thick case. And the outer disk, of course, it becomes optically thin, and it even drops below 0.01, which is a very good criterion for us to then test for what's called the vertical shear instability. The vertical shear instability is the hydrodynamic instability that we think drives turbulence of the order of alpha 10 to the -4, consistent with some of the observations that we're looking at with protoplanetary disks. So it's a very nice instability that works for fast cooling timescales. And we see that in the outer part of the disk, we might even be vertically shear unstable here. The dotted line is the critical cooling time given by the Lin and Uden criterion for the vertical shear instability. And we see these finger-like modes that in the vertical velocity, and some even midplane mixed modes here. But of course, we don't have the resolution to capture the proper saturated state of the VSI with these particular models. And because our models favor shadows in the more optically thicker cases, we would think that, of course, the cooling time scales much longer, and hence they might not even be VSI active. But for our fiducial case, we do see evidence of these vertical velocity signatures very much akin to VSI-like finger modes. And that brings me to like a short summary that we find a region of the disk where we can form these starlight-driven shadows, and these are more favorable for optically thick and slowly cooling disks. And these can correspond to deviations in the optical and IR emissions, creating bright and dark rings exciting for things that can drive substructure from surface to the midplane. And the future work includes multifluid dust and radiation hydrodynamical modeling. And these results are part of this paper that I published this year, so you can have a look at it. And before I conclude, I would also like to talk about, of course, the future work that we've been doing. So there are some preliminary results with dust and radiation that we've been doing. This is for a single dust, 10 micron dust, and we have hydrostatic simulations now. What we're seeing is something that's interesting. So for different dust diffusivities, we see that the irradiation absorption surface becomes extremely thin. And because it's so thin, we're not able to see any waves that are forming. So we think that we see this superheated dust layer and a very small irradiation absorption surface, and we don't actually see any bumps here in the hydrostatic case. But of course, this is not so realistic because we just have a single dust scale height and then we're forcing the dust densities. And this needs to be done with much better drag and back reaction and opacity feedback and hydrodynamics that need to be included. And that brings me to the multi-fluid dust module that we have in PLUTO. So we have a pressureless dust fluid module that we're going to be using to test this particular problem in the near future. So we've been working on this module for some time now, and I'm happy to say that this module will be publicly available in a few months as soon as we are done with the paper. And these are some results for the streaming instability. So the streaming instability is a classic dust drag instability, which we use to form planetesimals very nicely in disk simulations, and we show that the AB and BA tests that are very well tested classical shearing box tests work very well with our current implementation of the pressureless dust fluid. This has also been resolution tested. And I would also like to show some of these 1D models that we have for the radial velocity test here, and to show that for different Stokes regions, so the Stokes number depicts how well your dust and gas is coupled. So for very small and for very large Stokes, we have implicit and explicit solvers that we get back very good results for, very good match to the analytical solutions. Of course, if you go higher and higher Stokes, the pressureless dust fluid method itself starts breaking down. So you need to be careful with that. But for nominal Stokes, the dust fluid method is still very useful, and especially coupling with things like coagulation and radiation hydrodynamics, which we want to do by consistent opacity updates with as the dust dynamics changes. And this is also like a simple dusty wave test where you have a dusty sound wave that damps in time to show that the dust gas coupling tests work pretty well for the different Stokes regimes. Currently, we also have the tests that I showed right now are for the drag solver. We also have some results for the dust diffusion solver. We're currently benchmarking the different approaches that are used between the different codes. So all of the codes are solving slightly different equations. So we're trying to test them all and see what differences are between the different codes. So that's part of the upcoming paper that I'm working on. But otherwise, the plan is to then use this multi-fluid module and then test the irradiation instability, the starlight shadowing scenario more robustly in the future. And that brings me to the end of my talk. I'm going to keep my summary slides over here. And I'd like to thank you again for listening to me go on about things that I like talking about. So I'm happy to take any questions. Thank you so much.